Today we're going to talk about waves, and waves are very much tied into simple harmonic motion, as we saw with the pendulum and the mass attached to the spring. That motion is a back and forth motion about equilibrium position, and a wave is pretty much the same type of motion. Now, a wave is a disturbance moving through space and time that is transmitted progressively from one place to the next with no net transport of matter. What that means is that matter doesn't follow it. Right now, you are hearing sound coming out of your computer, and that sound is a wave. And what's happening is the air is not moving from the computer to you. The vibration traveling through the air is. So the air is just a way for the sound to move through, but the air doesn't have to move with the sound. Now, there are different types of waves. We have a pulse, which is a single non-periodic disturbance. That means like a one-time shot. Whereas periodic is a repeated periodic motion. An important one with this is, of course, that it repeats. So it's again and again and again. So me talking, if I just went, that'd be a pulse. But if I went, that's more of a periodic type of motion. Now, one type of wave is called a transverse wave. A transverse wave is where the motion of the medium is perpendicular to the motion of the wave. Now, in this case here, the wave would be moving from, let's say, left to right. And the whatever's carrying the wave would actually be moving up and down. And so let's say this was a water wave. A water wave is a type of transverse wave. If this was a little bit of a water molecule here, it would just move up and down, up and down, and up and down while the wave went from side to side. So the water is a medium through which the wave would be passing through. Now, let me go forward and back here for a second. Different parts of this wave. Wavelength is the length from a crest to a crest, or a trough to a trough. Trough are the lowest points, crest are the upper points. Amplitude is how far it's displaced from the equilibrium position. And for this case, think about equilibrium position as what would it be like if there was no wave there. And so this is a transverse wave. The medium is moving perpendicular to the motion of the wave. The wave here is moving left to right, but the medium is moving up and down. Different case of this is a longitudinal wave, which is where the motion of the medium is in the direction of the motion of the wave. Sound is a longitudinal wave. And we can see a case like this where we see this wave is moving because there's a piece where it's stretched out, then there's a piece where it's compressed together, and the piece where it's stretched out, and then it's compressed together. And this is actually the wave would be moving from one side to the next. And if I was one of these little pieces of springs here, I would actually be moving kind of side to side with it. So the medium is moving in the same direction that the wave is. So this is a longitudinal wave. Now, as I'm talking to you, that's a sound wave. The molecules are vibrating back and forth from me to you. And so that's a longitudinal wave. And in this case here, a wavelength would be from a point of compression to a point of compression, or a point where it's spread out to a point where it's spread out. Now, an important thing to remember here, and this is just a big thing, so that's why we have one whole slide for it, is that waves transfer energy, not matter. I'm talking to you, but I'm not sending air your way. Instead, I'm sending energy your way. So the energy is moving from me to you. It's just passing through that matter to get there. So the matter doesn't move. Well, I mean, it may vibrate, but it doesn't flow outwards. There was an old-time commercial where you had a household situation. You had a giant speaker here. It was cranked up as loud as it could go, so you had a big speaker here. And then you had like a dog. So I'm going to draw my dog. So that's my dog. See? It says dog. And they had it such that like the dog's ears were being blown back by the force of the sound. They say our speakers are so powerful they'll blow you away. But the problem with that is that the sound does move away from the speaker, but the air just vibrates back and forth. It doesn't really move very far, and so it's not like being in a wind tunnel. And so that was a really bad commercial, physically speaking. Now, just a couple terms that we need to know for today. Wavelength is, of course, the length of one complete cycle from crest to crest or trough to trough. So crest to crest or trough to trough. So high point to high point or low point to low point. So crest is the highest point, the largest positive amplitude. Trough is the lowest point of a wave, largest negative amplitude. And of course, amplitude is just displacement from equilibrium. So if we think of our standard sinusoidal wave, here's a crest, that's one wavelength. And here's a trough to a trough, and that's one wavelength. Now, the symbol for wavelength is lambda. So when we're talking about wavelength, it's a measurement of length. The length of a wave, that's the symbol we're going to use. So, know it. Now, period and frequency, we talked about these with the pendulum. Period, of course, time takes complete one cycle. Frequency is how often cycles per second, and they share inverse relationship. And frequency, of course, is measured in hertz. Period is measured in seconds. Now, wave speed is how fast a wave propagates, move outwards from the initial point. And there are some things that can impact wave speed, but a nice little equation for wave speed, and there's our nice little symbol for speed, it's equal to the frequency times the wavelength, which, can also be equal to wavelength divided by period, because that's what frequency is. So we can use this to calculate the speed of a wave. Frequency and the wavelength equals the speed. Now, how fast a wave moves through depends on what's producing the wave. It also depends on what it's moving through. Right now, you're listening to me, and sound moves at different speeds through different mediums. It moves more quickly, like, let's say, through a more solid object like your desk or through water, than it does through air. And it even moves at different speeds through air at different temperatures. And we'll get more to that later down the road with a very cool lab. So, basic stuff we're seeing here today right now. Wave speed, that's really our only new equation to deal with. Lambda here is talking about the length of a wave. Typically we do measure that in meters, but you just pay attention to the units and you'll see meters per second, centimeters per second, or what. Now, I do want you to have a couple problems to look over this. So place these into your notes. We'll go over this hopefully either Friday or Monday. So page 457, 1 through 3, and these are just dealing pretty much with these types of problems. And check the back cover of your text if you forget what the symbols are for, like, let's say micro, or in the case of mega, as far as scientific notation, because you will see those in these problems. So work on those. We'll go over that on Friday, and I'll see you then.